Many plant processes are monitored and regulated by some type of process control system. A process control system monitors the value of a process variable and provides actions that control the value of the variable. Two basic types of process control are manual control and automatic control. With manual control, an operator monitors the value of a process variable and then manually makes whatever adjustments are necessary to control the process. Automatic control is basically a form of control that's performed with little or no human intervention. To get a better understanding of how an automatic control system works, we'll use this simplified illustration of a system that's used to control the level of water in a tank. Since the level of the water is what's maintained at a desired value, it can be thought of as the controlled variable in the system. It can also be thought of as the measured variable, because the control system uses it as a basis for making operating changes. The level of the water will remain constant as long as the flow of water into the tank equals the flow of water out of the tank. In this system, the water level is controlled by regulating the flow of water into the tank. For that reason, the flow of water into the tank is called the manipulated variable. As with all automatic control systems, this system has four basic parts or elements. One element, the primary element, is a sensing device that's located where the process variable is monitored. In this system, the primary element is a float that senses the level of water in the tank. The float is connected through a mechanical linkage to the second element in the system, a measuring element. In this system, the measuring element is a transmitter. The transmitter detects the position of the float and transmits a signal representing the level in the tank to the third element in the system, a controlling element. The controlling element, or controller, measures the signal from the transmitter, compares the signal to the desired level setting, computes any difference between the two values, and if necessary, produces a corrective signal. The controller sends the corrective signal to the final control element, which in this case is a control valve. The control valve adjusts the flow of water to the tank as needed to keep the level at the desired setting. When a process is operating normally, the variables for that process will be at or near their desired values. The desired value of a process variable is known as the set point. For example, the set point for the water level in this system is 3 feet. When the values of the process variables in a system remain relatively constant over a period of time, the system is said to be operating under steady-state conditions. Most control systems will allow slight variations in the values of process variables. But if the value of a variable changes significantly from its set point, corrective action may be needed to return the process to its original operating conditions. To see how a process disturbance can affect a control system, let's look at the automatic level control system that we saw earlier. In this example, a process disturbance causes a decrease in the demand for water from the tank. The decrease in demand causes the level of water and the float to rise. In this case, the water level rises to 4 feet. The movement of the float is transferred through the mechanical linkage to the transmitter. The transmitter then sends a signal that's proportional to the increased water level to the controller. When the controller receives the signal, it measures the signal, compares the measured value to set point, and computes the difference between the two values. The controller then sends a corrective signal to the control valve. The control valve responds to the signal from the controller by closing to reduce the flow of water to the tank. This compensates for the decrease in demand that caused the water level to rise. As a result, the level returns to its original set point value of 3 feet. The transmitter is the measuring element in this system. It detects the position of the float and transmits a signal representing the level to the controlling element. One of the basic methods of control used by automatic process control systems is feedback control. In a feedback control system, a control action is initiated after the controlled variable has deviated from set point. To see how an automatic feedback control system works, we'll use this illustration of a heat exchange process. In this system, steam is used to heat water. The steam enters the system through a valve, then flows through tubes inside the heater, and exits the heater through a pipe on the other side. The steam transfers heat to the water, which enters the heater at the top, flows around the tubes, and exits the heater at the bottom. The temperature of the water at the outlet of the heater is the controlled variable for the system. It's also the measured variable, because the control system uses it as a basis for making operating changes. The manipulated variable in this system is the inlet steam flow. That is, the steam flow to the heater. It's adjusted to keep the outlet water temperature at set point. The primary element in this feedback control system is a temperature sensing device in the outlet water line. More specifically, the device is a temperature sensing bulb, which contains a gas. If the temperature of the water leaving the heater increases, the gas in the bulb expands. This causes a pressure increase that's carried along the tubing connecting the bulb to a temperature transmitter. The transmitter sends a pneumatic signal that's proportional to the water temperature to a controller. The controller measures the signal and compares it to set point. This is how the controller detects that the temperature of the water has increased. The controller then computes the difference between the temperature of the water and set point and sends a corrective signal to the final control element in the system, which is the control valve. The control valve responds to the signal from the controller by closing to reduce the amount of steam flow to the heater. As a result, less heat transfer takes place in the heater, and the outlet water temperature returns to set point. A feed-forward control system attempts to correct for a process disturbance before the controlled variable in the process deviates from set point. To get a better understanding of how a feed-forward control system works, let's look at an illustration of a heat exchange process that's controlled by a feed-forward system. In this system, steam flows through tubes inside a heater and heats water that flows around the tubes. The controlled variable in the system is the water temperature at the outlet of the heater. The inlet water temperature is used to determine whether a control action is needed to maintain the outlet water temperature. So it's the measured variable in the system. The manipulated variable, that is, the variable that's adjusted to maintain the outlet water temperature, is the steam flow into the heater. The feed-forward control system works like this. If the temperature of the water entering the heater changes, the primary element in the system, in this case, a temperature sensing bulb, detects the change in temperature and changes the signal that it sends to a transmitter. The transmitter measures the signal from the temperature sensing bulb and sends a proportional signal to a controller. The controller measures the signal from the transmitter and compares it to set point. If there's a difference between the two values, the controller sends a signal to the final control element in the system, the control valve. The control valve responds by opening or closing to change the amount of steam flow to the heater. If the temperature of the water flowing to the heater decreases, the control system opens the control valve to increase the steam flow to the heater. This provides more heat for transfer to the water and prevents the outlet water temperature from dropping below its desired value. Now, if the temperature of the water entering the heater increases, the control system closes the control valve to allow less steam to enter the heater. As a result, less heat is transferred to the water, and the outlet water temperature is kept from rising above its desired value. A feed-forward control system can be effective at correcting for certain process disturbances before the disturbance affects the controlled variable in the process. However, there are many possible disturbances in a process, and a typical feed-forward control system may not be able to respond to every one of them. For example, the feed-forward control system that we just looked at responds only to changes in the temperature of the water entering the heater. Other disturbances, such as a change in the pressure or temperature of the steam entering the heater, can also affect the outlet water temperature. But those disturbances will go unnoticed by the feed-forward control system. To correct for those types of disturbances, a combination of feedback and feed-forward control could be used. With combined control, the feed-forward part of the system responds to changes in the inlet water temperature, while the feedback part responds to changes in the outlet water temperature caused by other disturbances. By combining the features of feedback and feed-forward control, greater control over disturbances upstream of the process and within the process can be attained. In this topic, we saw how the four elements of an automatic control system work together to control a process, and how a control system responds to a process disturbance. We also saw how feedback control, feed-forward control, and a combination of the two methods work to control a process. Now let's try some practice questions related to this material. Write. The controlling element, or controller, computes the difference between the measured level and set point, and sends a corrective signal to the final control element. No. The controlling element, or controller, computes the difference between the measured level and set point, and sends a corrective signal to the final control element. The controlling element, or controller, measures the signal from the transmitter, compares the signal to the desired level setting, computes any difference between the two values, and if necessary, produces a corrective signal. The controller sends the corrective signal to the final control element, which in this case is a control valve. One of the basic methods of control used by automatic process control systems is feedback control. In a feedback control system, a control action is initiated after the controlled variable has deviated from set point. A feed-forward control system attempts to correct for a process disturbance before the controlled variable in the process deviates from set point. All processes have characteristics that can affect how a control system responds to operating changes. Two of the more important of these characteristics are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in describing electrical circuits, they can also be applied to process systems that contain fluids. For example, in this system, the resistance is caused primarily by a valve that opposes the flow of liquid from a container. The system's capacitance, or ability to store energy, is determined by the size of the container. These same characteristics can also be applied to gas or vapor systems. For example, in this system, the resistance is caused primarily by a valve that opposes the flow of gas from a pressurized cylinder. The capacitance depends on the storage capacity of the cylinder. Now, in a thermal process, that is, one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. The amount of heat or thermal energy that the liquid is able to store represents the capacitance of the system. Process characteristics such as resistance and capacitance can affect how a control system responds to process disturbances. We can get a better understanding of how these characteristics can affect a system by looking at an illustration of a simple heat exchange process. In this system, steam flows through tubes in a heater and heats water that flows around the tubes. At the moment, the temperature of the steam entering the heater is 400 degrees Fahrenheit, and the temperature of the water leaving the heater is 200 degrees Fahrenheit. Now, suppose a process disturbance causes the temperature of the steam to suddenly rise to 500 degrees. What do you suppose will happen to the temperature of the water? Even though the steam temperature increased suddenly, the water temperature will remain unchanged briefly, then increase slowly. It's easier to see how the water temperature changes by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input or a step change. When we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. In the heater, the transfer of heat from the steam to the water was delayed because of resistance to heat transfer through the tubes, and because of the water's capacitance, or the ability of the water to store heat. Another factor that can contribute to dead time is the distance that the heat has to travel to reach the temperature gauge. In this case, the greater the distance from the heater to the gauge, the greater the dead time. Looking back at the graph, we see that after the time delay, the water temperature gradually rose to a new value of 300 degrees. The total amount of time that passed from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag time, or lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance. In this topic, we focused on certain characteristics of a process that can affect a control system's response to a process disturbance. Now let's try some practice questions that relate to this material. All processes have characteristics that can affect how a control system responds to operating changes. Two of the more important of these characteristics are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in describing electrical circuits, they can also be applied to process systems that contain fluids. The total amount of time that passed from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag time, or lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance.